We are done with the members that were going to be loaded axially, that is in the case of tension or in the case of compression. In both these cases, the length of the member will going to change, and the change in length is given as a dl is equal to F multiplied by L divided by A divided by E. If we draw here the grid before and after the loading, you will find that the element will deform along the direction of the force, and we have linear strain is produced, that is called as normal strain. And the normal strain is given as the stress divided by the Young modulus if the material is elastic. And if we have a cross section is equal to A, in that case we can define the stress will be equal to force upon area. Then we have introduced the two-dimensional and three-dimensional Hooke's law. Then there are the members that instead of being pushed or pulled like tension and compression, these members are going to be bent, that is called as bending. So we have a simply supported beam here, a pointed load will act exactly at the center, so both reaction RA and RP are equal is equal to F by 2, and we will get a maximum bending moment at the center. Because of the bending, the stress produced on the top fiber will be compression and bottom fiber will be in tension. This will give the flexure formula. According to the flexure formula, we have bending moment M divided by second moment of area, that is the moment of inertia, is equal to bending stress at any distance y, so sigma b by y is equal to Young modulus divided by radius of curvature equal to rho. Using this, we can find out here bending stress for different sections if we know the moment of inertia of that section. In addition to this, already we have finished the deflection under the constant force in the case of simply supported beam. So this deflection delta value also we are knowing it. In this video, we are going to discuss the torsion. So consider here a shaft which is subjected to twisting moment T. Let L be the length of the shaft or the circular bar, and the D is the diameter of the bar. For simplicity, the left end is fixed to the wall. What we are interested in the case of torsion, what is the torque required, what is the shear stress produced, what is the angular deformation theta, what is the shear stress produced tau, what is the relation between shear stress tau and theta, and other material property, and what is the value of the shear strain produced. So these are the objective in the case of torsion. So when members are loaded with a moment above the longitudinal axis, they are said to be in torsion, and the applied moment is then called as torque. This situation is common in the shafts that transmit the power in the screw fasteners, and in many situations where the applied moment vector is parallel to the long axis of the part rather than transfer to it, as in the case of bending. Number of times this torque is also represented by double arrow, which is representing the torque, and you have to follow the right hand rule convention. So this figure is showing you a straight bar having a uniform cross section, that is a circular cross section with a pure torque applied in such a manner that we have bending moment Bm will be equal to 0 and no axial force or transverse force is acting. So transverse force, that is the shear force, will be equal to 0. The fixed end of the bar is embedded in the rigid wall and the bar twists about its longitudinal axis. So this bar is going to twist. Initially we have point A before we apply the torque, and after the position of the A will change to position A prime. In that case, the angle turned by this plane will be equal to theta, that is called as angle of rotation. We are interested to know what is the angle of rotation, what is the shear stress produced, where the shear stress is maximum, whether it is maximum on the outer fiber or the inner fiber, what type of distribution we have. Like in a bending stress, we have linear distribution. So we are also interested to know what type of distribution we have in the case of torsion, and also interested to know the value of shear strain, just like a normal strain in the case of axial loading and the bending. So in general, we'll define the shaft as a rotating machine element which is used to transfer the power from one point to another point. Their cross section can be either a solid or can be hollow. or a combination of a solid and hollow, that is called as a composite shaft, or they can be round or square or some other cross section also. But as far as we are considered, we are only interested in the circular cross section, that is a round, and we are interested in the solid and hollow. Normally the solid shaft is used to transmit the power for a shorter distance, and if the distance will increase, naturally the cost involved will be higher, and their hollow shaft are normally the propeller which is used in the case of trucks or heavy transmission system. Propeller is a hollow shaft. For normal shaft, we normally use the carbon steel, and for high strength we're going to use the nickel chromium alloy, can also be used for high strength. Shafts are manufactured either by hot rolling or by machining or by cold rolling and the drawing. Similar to the shaft, we have axle, but shaft is rotating and used to transmit the power, whereas axle is a stationary shaft which is subjected to bending moment and it acts as a support. It is not a rotating member, it's just a stationary member. We can find the axle in a car, we can find the axle in bikes and the cycle also. If the length of the shaft is very short, then it will be called as spindle. Spindle is normally used in the case of drilling machine, and it will transmit the power to a cutting tool. But basically we are interested in the torsion, where we don't have any type of bending moment, any type of shear force, that is a transverse load, and what we are interested in the value of the theta, that is the rotation or twist, then the shear strain, then the shear stress distribution and the torque. So here we start the theory, that is the torsion formula we'll discuss now. Now before we discuss our torsion formula, we'll consider here a certain assumptions, and using this assumption we'll derive the equation. So the torsion theory for axisymmetric section, that is a circular section, we're going to use. The torsion equation we'll derive will apply only to the axisymmetric sections like a solid circular or the hollow circular sections. We'll make the following assumptions while deriving this equation. First assumption is that the sections that are plane before twisting will remain so after twisting and do not wrap, and the circular section remains circular after twisting. So initially, before we apply the torque, we have shown here the section, and we have drawn here the grid by drawing the horizontal line and the circular line, and these are, we will find here a circular sections. So these circular sections are drawn here to understand how exactly the shear strain is produced. And in addition to this, we have drawn here the horizontal lines. These lines will be get twisted as you apply the torque on the shaft. So let's apply a twisting moment here. So we are applying a twisting moment in this direction, and we observe here what exactly the changes will take place in our grid formation. So this one is action, so you have to show here a reaction. So reaction torque you have to show always in opposite direction, so that the net torque will be equal to 0. So as far as the circular section is there is no change in the circular section. Circular section before and after the twisting is remains same. So there is no change in the circular section. But initially the line which was a straight line here, now this straight line here will become slightly twisted, and therefore it will be a shear strain will form over the outer surface, and we'll find here that is a twisting is produced inside this region. So when the shaft is twisted, the angles are no longer 90 degree. The rectangles have distorted or sheared into parallelograms. So let's consider here one rectangle. So this rectangle you observed before twisting, and the same rectangle here we'll find here that the edges is slightly, these edges are now at a certain angle. Initially they are horizontal and now they are get twisted. Let me represent like this. So after twisting you will get the effect of this one. So this one is the action due to shear. So this time the shear stress will act. We are interested to know the value of the shear stress. Then what is the value of the shear strain? That is equal to gamma. Gamma is formed on this edge, that is on the lateral surface, that is on the peripheral surface, and this is the circular cross section where we have a twisting takes place. So if I show this horizontal line and if I join with the center, then I will get this one is a dotted line which was the initial position. Now the same line I will show here. So initially it was horizontal line, and now it will be get twisted by a very small angle equal to theta. So this one is the angle of twist. So I had drawn here two horizontal lines here. Both the lines are here horizontal, but before the twisting it's a horizontal, and after twisting the same horizontal line is get twisted. Now it is twisted according to this direction. So on this plane, whatever the angle is formed, that will be called as shear strain. That is represented by gamma. So we'll develop here the equation between gamma, theta and the shear stress tau. The third assumption is that the straight radial lines in a transverse section remain straight after twisting also. So these are the straight lines here, that is the before twisting. These are also a straight line after twisting, but they are slightly get rotated by certain angle depending upon the value of the shear strain. The fourth assumption is that the stresses in the material, that is the shear stress developed in the material, do not exceed the proportional limit. Now since we are familiar with the proportional limit and the material property, this time the graph is drawn versus the shear stress versus the shear strain. Initially we have a straight line distribution shape, and then we have non-linear, and then we have strain hardening, and then we'll get the value of ultimate corresponding value up to where we have linear distribution shape. That will be called as the proportional limit, and this proportional limit is simply taken as SYS, that is the yield stress in shear. So basically there is no difference in the upper yield point and the lower yield point, so SYS will be the limit we'll take here, and we have linear distribution here. The elastic property here will be the modulus of rigidity G, and is given as the stress, that is the shear stress divided by shear strain, almost same as the Young modulus equal to E is equal to normal stress sigma divided by the normal strain equal to epsilon. So this is our assumption that we always work below this limit. Anywhere below this one, this relation is always true. So we can use the equation that modulus of rigidity G is equal to tau, that is the shear stress divided by shear strain. Only this limit we will consider, that the part is working below the proportional limit, that is the value of SYS. So first we develop the equation between the shear strain and the twist angle equal to theta. So let's say T is the torque or twisting moment, R is the radius of the shaft, L is the length of the shaft, and theta is the angle of twist. Let's say this one is the center here, and I draw here a horizontal line. Let's say this line is OA line. So when we apply the torque here, what happened to this line? This line is get twisted, and finally the point A will come to the position A prime. That is, you will get here the change of A from A to A prime. How much angle it has been turned, that is this angle, is called as twist angle equal to theta. Now this one we have discussed about the face, that is a cross section. Now what about the surface here? So say, I will draw here one horizontal line on the surface of radius equal to R, that is on outer periphery. So this line represents here a line parallel to the longitudinal axis before we have a twisting, and once we apply the twist here, the point A will come to A prime. That is on the surface also you will find the twisting of these lines which are parallel to the longitudinal axis, and whatever the angle formed in this case here, that will be called as the shear strain equal to gamma. Now since we are working here on the outer fiber, we'll call this one as gamma R. So actually this angle formed is very small, and we have the distance traveled by A to A prime can be approximated equal to H, which is same as the sector length here. So approximately we can say here the value of H is same as equal to A prime, and this distance can be approximated as H equal to, since the point A here is on the radius equal to R, so it is R multiplied by theta, where theta you have to take in radian. On the side view here, this angle formed is equal to the shear strain, that equal to gamma R, This one is the length equal to L and this distance equal to H. So the same distance H we can write as a product of the shear strain multiplied by length L. Here also you have to take the gamma in radians. So we have two equation of H, that is the displacement of A from A to A prime. And we can develop here the relation between the shear strain and the angle of twist theta. So from 1 and 2 we get here H is equal to R multiplied by theta is same as equal to gamma R multiplied by L. Or we can write here as theta divided by L is same as equal to gamma, that is the shear strain at outer radius divided by the radius R. So whenever we apply the twisting, we'll find here initially we have the shape of the piece is rectangular and it becomes a parallelogram. So it becomes a parallelogram like this. This is purely the effect of shear. So if we consider here a rectangular element, then it becomes a parallelogram due to application of a shear stress. The horizontal edges will be inclined with the horizontal at an angle equal to gamma. That value of gamma will be called as shear strain. So gamma representing here the shear strain on the outer periphery. So here we successfully develop the relation between the angle of twist theta and the shearing strain gamma. So gamma represent here the shearing strain on the outer surface. Then we have value of theta divided by L is same as equal to gamma R divided by radius R. This value of H we can write as theta multiplied by R, and same value on the other side we can write as gamma R multiplied by length L. Rearrange this, we will get the expression for theta by L is equal to gamma R divided by R. Now this one is a situation where we have a shear strain is occurring on the outer surface. Now what exactly happens if I consider here the inner core at any radius R? Whether the value of theta will change or the value of gamma R will change, that is the shear strain will change if I take the inside core. That will verify, and then we'll make a generalized equation for shear strain. So as far as the outer surface is considered, the point A to A prime, this distance is A to A prime is given as theta multiplied by R is same as equal to gamma R, that is the shear strain of the outer surface multiplied by length L. So we get here theta by L is same as equal to gamma into R divided by R. Naturally, we want to develop here the generalized equations. I will consider here one core and I will show that figure separately to you. So imagine that we have a core here of radius equal to R. This surface is radius equal to R. So again I take here one point equal to B. So I will draw here horizontal line with the center O, and one point I will take as a B, that is on the core. And because of application of the twisting moment, the point B will shift to B prime. So this point is same as equal to B prime. Now exactly here the same thing is happening here. So this angle will be same as equal to theta. That is, we have B to B prime, we get a same angle equal to theta. So this one is B, this one is B prime, and we have same angle is theta. Only thing that this time the radius equal to R. And when we are on outer surface, then the point is represented by A, and A will change to A prime. So this one is a A prime. This one is the sector we are showing. This one is the outer surface and this one is the inner core. Now the same line, horizontal line, I have shown here to represent the value of shear strain for the core. And since the point B has been shifted to B prime, you will get here different value of the shear strain. Let's say this value of the shear strain equal to gamma suffix lowercase r. So this one is the same, our reference length equal to L. This one is a dotted line representing the position of point B to B prime. And this angle we are calling as gamma suffix r. That is called as local shear strain, or the shear strain at radius equal to r. So again this time the value of BB prime will be equal to gamma suffix lowercase r multiplied by length L, and from this figure this one is radius r, so this sector length will be approximately equal to theta multiplied by r. Again we can develop the equation here as theta divided by L is equal to the shear strain at any radius r divided by r. This one is our equation number 2 and this one is our equation number 1. This equation is representing on the surface and this equation is representing on the core. So gamma suffix lowercase r represent here the shear strain at any radius r, and we have limit of r is from 0 to uppercase r, which one is at a outer fiber. So two equation form here, equation 1 and equation 2. So we get here theta by L from equation 1 and 2 is same as the shear stress on the outer surface is gamma r divided by outer surface radius equal to r is equal to the shear strain at any radius r divided by r. Now since here the value of the r will be maximum is equal to capital R, so what we'll do here, we'll represent the value of gamma r, which one is the maximum possible value because we have limit is from 0 to capital R. So this value of gamma r will be the maximum value as gamma into r will be called as is the maximum value of the shear strain. So gamma suffix r represent here the maximum outer surface is at radius equal to capital R. Corresponding the shear strain is maximum and is called as the maximum shear stress. So hereafter gamma suffix capital R will be represented as gamma max, and since this value of r is dependent on radius r, so hereafter we'll replace the gamma suffix r as a function of radius r, that is we write this value as gamma as a function of r. So this one is representing the function of r. So finally we conclude the first part about the shear strain at any radius r and the maximum value of the shear stress for any inner surface. We have theta by L is equal to gamma sub r divided by r. Gamma of r represents the function of radius r, that is the value of the shear strain is a function of radius r, and the maximum value of the shear strain will occur on the outer surface, that is the value of gamma r. So this value of gamma r will take as gamma max. So this equation we can write in general as theta by L is equal to gamma, which one is a function of radius r divided by radius r, is equal to gamma max divided by outer surface radius equal to r. And therefore shear strain at any radius r, which one is a function of r, in general is given as gamma maximum multiplied by r divided by capital R. Remember the limit of r is from 0 less than equal to r less than equal to capital R. Second part will continue in the next video, that is the distribution of the shear stress, relation between shear stress and the torque, and then we'll develop the torsion formula. The video you are watching is from the app, which is the Mohod class app available on Google Store, and in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.